Sorry about that. My power just went out right when I was finishing up talking about this. So the noble gases all have a full valence shell. So all of them have a valence shell of 8. However, helium has 2. But if you remember the first orbit, so here's our nucleus. The first orbit can hold a maximum of 2 electrons. So technically it is also full at only having 2. Now, noble gases are the most unreactive elements on the periodic table. And the reason why is because remember that the whole reason why elements undergo chemical reactions is to become stable. So elements that are already stable, of course, will be unreactive. Okay, majority of them are colorless, odorless, and of course, we already talked about unreactive. Okay, and a lot of them were actually very difficult to discover, as you can imagine, because they're not found in any sort of compound or molecules. They're on their own, and they're all gases, of course. So the next part to this still coincides with elements in the periodic table, but we're going to go a little bit more into the elements. Okay, so just kind of recapping the definition of what is an element. So elements are pure substances that cannot be broken down into simpler substances by chemical means. They're composed of one kind of atom. So, for example, sodium, carbon, iron, right? So we're assuming that this is a pure substance. So if I have a chunk of iron, I'm assuming that every atom that is inside of that chunk is made up of the same type, right? Same type of particle, which is an element. A compound is where we can have more than one element that is chemically connected. So when you're looking at the chemical formula, right, remember an easy way to remember that is you see more than one capital letter, right? So meaning, so H2O, right, it has hydrogen and oxygen, right, that have been chemically combined to make one compound. So compounds are also pure substances. So meaning, let's say I have a glass of pure water, I'm assuming that every single molecule that is there or compound that is there is H2O, right? So pure substance just means you have the same type of particle. An element is where you have, if you remember your particle pictures from grade 9, especially if you had me as a teacher, I'm sure you remember them, right? So an element is where you have the single circles, whereas a compound is where you would have circles that are combined. Right? They can be the same element or different elements, but pure substance just means that in this type of matter, they're all the same, right? The particles are all the same. Mixtures is when you start bringing different things together, different types of particles. So naming elements, so the regulating system that actually is responsible for the element naming is IUPAC, so the International Union of Pure and Applied Chemistry. These are also the same governing body that determines symbols and units. So if you remember from our introduction unit, we talked about, for example, grams or milliliters, like who came up with these names and these quantities and the symbols and all that. Same people, okay? So it's an international system that is the same worldwide, right? So if you're looking at a capital letter C for an element, that's carbon, no matter where in the world that you are reading the periodic table from. So where do elements get their names? So from a variety of sources. To be honest, most of them are either derived from their Latin or Greek name, which I believe, did I not write that in there somewhere? No, I did not. Okay, so anyways, their Latin name. So for example, right, so Fe for iron comes from ferric, right, which is a Latin term for, of course, translated to English, is iron. So it can be named for Latin, Greek terms, where they're discovered. So for example, californium or europium, germanium in Germany. Or sometimes it's also to pay tribute to a scientist. So I always like looking at the periodic table. It's kind of like, having a star on the Hollywood Walk of Fame, but, much more noble than that. I like to think that Einstein's a little bit more popular than Reese Witherspoon or something, but but anyway, so Einsteinium, curium for Marie Curie, borium for Bohr, Rutherfordium. There's lots of scientists' names that are up there. So remember, those are not the people who actually invented or discovered that element. It's kind of like I said, it's like a tribute or like an honor to have an element in your name. So Mendeleev was the chemist that was first responsible for organizing the periodic table. So the periodic table kind of goes through what he coined as being the periodic law. So meaning elements that are arranged in order, when elements, are arranged in increasing atomic mass, what happens is there is periodic repetition of properties at regular intervals. So meaning elements tend to have properties that are grouped together depending on the placement on this periodic table. So actually we already looked at examples of that where we looked at the groups on the periodic table that have similar characteristics, right? They're part of the same chemical family. So it kind of has to do with the arrangement of those elements, right? It kind of wasn't just put together randomly in that order. There was a rhyme and a reason for it. So we have them based in order of atomic mass in vertical columns. And then, of course, later it was arranged horizontally. So it's essentially the vertical columns were periods before, but now we have our periods going left and right, and our columns are now known as our groups. So hopefully this is clear. So the atomic mass used to go up and down, right? 1, 2, 3, 4, 5, 6, 7, 8. But now they go across, right? So if we go back, I actually don't have the periodic table there. It's in the next slide. So going from left to right is the order of atomic mass currently, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm reading off the atomic number, but the atomic mass increases this way as well. So it's in order of increasing atomic number as well as atomic mass. So elements with similar properties are in the same column or group, which is exactly what we mentioned, and it creates trends. We will be going through some other trends that are on the periodic table. Those are not the only ones, but just for now, so that you know that there is a reason why things are put together the way they are. There is, again, a reason for everything on here. And if you continue in grade 12, you'll notice that there's even more so of a underlining meaning here. Now, of course, when Mendeleev first put this together, not all elements were discovered yet. So what ended up happening is he left gaps on the periodic table. So let me move this up here so you can see that a little bit better. So if you notice, the different colors tell you kind of the timeline of when things were discovered. So I always like bringing the attention to scandium here. So notice all of these elements in blue that are kind of surrounding here were already discovered by 1843. So when this was put together, there was a gap that was left here. So the atomic number for this guy is actually 21. So calcium is 20, titanium is 22. So this gap was left. So we didn't know what 21 was at the time. I say we, like I was there in not that old, guys, so not in 1843. But, so this gap was here. So think of this as like an empty space. And then later on, when elements continued to be discovered, it basically filled in the gaps. Now, if that doesn't prove that this periodic table was meant to be organized in this way, I don't know what does, right? So imagine you're putting together a puzzle and you don't know what the end result is going to be and you can't find all the puzzle pieces, but you leave empty blanks in there, right? And then later on, as people find the puzzle pieces, they put them in until we have a complete picture at the end. It's kind of a beautiful thing, really. So just to review some terminology, so the modern periodic table, we have groups and we have periods. So remember when we refer to a group, it is a vertical up-down column. So there are 18 total on the periodic table. So we have 1 all the way to 18. And we've already talked about some of the groups that are here, right? They have similar physical and chemical properties. A period, of course, goes from left to right. So remember, there are 7 periods. And if you notice, the colors that match up are lanthanides and actinides fit in right here. Okay, and of course, the metals are on the left. And as we move to the right, it becomes less and less metallic and more non-metallic. And somewhere along here, we have our staircase, which is our next topic. So the staircase, we've already looked at this, is the zigzag line that basically is the boundary between metals and non-metals. And of course, the metalloids that are on that staircase, other than aluminum and acetine, have those in-between properties, so they don't really fit in one family, one part of one group of elements or the other, like metals or non-metals. Okay, so physical state. So whenever we're talking about the state of matter, it's always in reference to room temperature. Okay, so there is a term for it. It's called SATP. You're going to hear me say that quite a bit throughout the course of this semester and even into grade 12. So SATP stands for Standard Ambient Temperature and Pressure. Basically, in regular words, if you want to call it, it basically means room temperature and room pressure. So we're not talking about outside doing we're not talking about the temperature in winter or in summer. We're talking about essentially room temperature. Okay, so that's actually 25 degrees Celsius. So SATP, and the pressure of 101.3 kPa. Okay, we don't really need to know any of this right now. What I just want you to know is this is room temperature and pressure. So when I say at room temperature, magnesium is a solid, right? The physical state of matter is a solid for magnesium. So most elements, all the metals are solid except for mercury. Mercury is a liquid. Majority of our non-metals are gases. There are some solids, except bromine is a liquid. So typically on periodic tables, when you're looking at it, they'll have one color for gases, one color for liquids. Typically it's red for gases or like an orangey color, blue for liquids, and then most of them are black or gray font for metals that are solid. And that's about it. So when you are looking at a periodic table, of course, it's important to know the different properties, the different things. As we go through the course, you're going to notice that our periodic table that we're using in our course this year has more information on it than you've ever used before. As we continue throughout, we're going to learn all the different pieces and parts. All those numbers that are on that periodic table are there for a reason.